Hello all. So I'm going to give a SRC presentation on initial excitation based robust adaptive observer for MIMO LTI systems. So first, what is adaptive observer? So let us consider an uncertain MIMO LTI system which is subjected to unmodeled but bounded disturbances in the system and the output relation. So the important thing to note that the uncertainty in the state matrix A and the control matrix B is lumped in the unknown parameter vector theta. So in addition to the state and the bounded disturbance delta 1 and delta 2, theta, which is the plant parameter, is unknown. Uh, the information about A, matrix A, B, C, uh, the regressor, which is a function of U and Y, and the information about U and Y is known. So if the objective is that we need to estimate plant parameters and the state simultaneously, the solution lies with the adaptive observer. Though there are various adaptive observer designs for MIMO systems, I have enlisted a few important ones. So a thing is common in all these designs is that all these schemes guarantee parameter and the state convergence, but they require that the control needs to be persistently exciting, which is a restrictive condition. So, what is persistence of excitation? So, if we go by the definition of tau, n-dimensional vector phi is said to be persistently exciting if the following mathematical inequality follows, which says that the square matrix phi into phi transpose is positive definite if integrated upon a time window of finite time length capital T and shifting this time window in forward direction for all time. So this positive definiteness condition can be transformed to rank sufficiency condition, which says that if the vector phi is positive definite, then this square matrix is rank sufficient, and hence the signal phi can explore the whole of the n-dimensional state space, which is very crucial in getting the information about the unknown parameters. So with a motive to relax PE condition, a new concept of initial excitation is being introduced by Roy et al. So unlike PE, uh, in IE, the excitation requirement is in the initial time window and hence can be verified online. And because it doesn't depends upon the future value. So if we go to the definition, so the same vector considered earlier, so phi is said to be initial excitation if this square matrix phi into phi transpose is positive definite in the initial time window. So it is evident that it can be verified online since it does not depend upon the future value of the signal. So if we summarize the promises that existing observer schemes give, that they can guarantee simultaneous convergence of states and the system parameters, but they cannot guarantee convergence without the restrictive P condition. So the objective of my research is to get rid of this P condition for the design of the adaptive observer. So now revisiting the same system which I've discussed earlier. So here, as I already discussed, the state, the plant parameter theta, and the bounded disturbance, these are unknown. But these disturbances are bounded by an upper bound, which is known, and information about the matrix A, B, C, and this regressor, and information about U and Y is known. So an important assumption is considered, which is a standard one in the design of adaptive observer, which says that U is chosen such so that it is a stabilizing controller and taking the state and the controller to be bounded. So for the design of a robust adaptive observer, a two-layer filter based design is proposed, motivated by Lowenberger observer. So the original system can be rewritten as 4. So here the feedback gain K is such chosen so that the matrix A minus KC is Hurwitz, and the corresponding uh, state observer is given by 5, where nu t is an auxiliary signal, which can be designed subsequently, as we'll see in the preceding slides. And theta hat is the online estimate of the unknown plant parameter theta. Now, assuming the following relationship where theta hat is the, so I made a mistake. The suffix should not be theta, is x hat. So x hat is the estimate of the state. YF is the regressor, which is a time-varying matrix, and theta hat is, as I have just discussed, that it is the estimate of the actual plant parameters. Now, if we differentiate 6, the following relation is obtained, and if nu t is taken to be yf theta hat dot, the dynamics of yf can be obtained. So since a, k, c, and y, that is the right hand side of yf dot, all are known, so yf dot can be obtained online. So since 8 represents a stable low-pass filter equation with its input as y, so it is also called as the filtered regressor. Now, it is straightforward to get the dynamics of state estimation error given by 9, where theta tilde represents the parameter estimation error. So another auxiliary signal mu t, which is nothing but a linear combination of the state estimation error and the parameter estimation error, which plays a very crucial role in the design of adaptive observer. Discussed, the corresponding dynamic of mu is given by 11, and the solution of mu by 12. So now, linear parameterization. The novelty of the design lies in the linear parameterization that includes both the system parameters and the unknown initial condition as an extended unknown parameter vector, which facilitates the IE-based adaptive observer design. So, multiplying C on both the sides of the expression of mu, which is a linear combination of xl and theta as discussed in the previous slide, and using the expression of yf and mu, the following expression can be derived easily. And finally, linear in parameter form is obtained by 15, where z is the regressor and can be computed online. Now, this theta is very crucial, is the new extended parameter comprising of the unknown parameter theta and the unknown initial condition x. And delta represents a function of the bounded disturbance. Now, the right hand side of G is the combination of the known signals, so can be computed online, and the corresponding dynamics of filter error is given by 17. So to get rid of stringent P condition, a second layer of filter is introduced where YFF is the filtered regressor, since 18 represents a stable low pass filter with its input as the regressor Z. So YFF is a square matrix of dimension n p plus n plus p plus n. So it is very crucial in the design of the adaptive observer. So if we solve our equations 18 and 19, and with some manipulation, we can get this relation 20, which plays an important role in the design of adaptive observer, a filtered regressor. So if we look at the solution of the filtered regressor, two important properties can be seen. So first, that YF is a positive semi-definite function of time. And secondly, whatever the information about unknown parameter it gathers is lost at an exponential rate, and therefore kf is also called as the forgetting factor in the literature. So now the question is that how to secure this decaying information in the absence of P. So this motivates to go for switching. So switching basically captures the information rich transient signal and uses it for all future time so that the information decay does not affect the performance, and in the process makeover for the absence of P condition. So assumption 2 is simply an I condition on the regressor Z and is the cornerstone of the proposed work, which ensures a globally uniformly ultimately bounded stability in the absence of P condition. So for online verification of I condition, two lemmas are given by Roy et al. So first lemma says the necessary and the sufficient condition for the regressor Z to be I is that filter regressor YFF is positive definite, and once it is positive definite, it remain positive definite for all time less than infinity. So if we track the determinant of YFF and the moment it becomes positive, we can say, yeah, that filter regressor is initially exciting. So this is the parameter estimation law where L1 or switched, we can say switched parameter estimation law since this, so there is a presence of switch S. So L1 and L2 are the components derived from gradient descent method. So Li is the I term introduced by me where Q and P are the captured value of Y, FF and UF respectively the moment I is verified to be true. Well, sigma is the sigma modification term, which is very crucial in giving the robust design or to ensure robustness in the initial time window till the I condition is not satisfied. So the piecewise constants switching signal ST is defined as this. So this signal is very crucial in bringing in the I term the moment I condition is satisfied. So come to the stability analysis. So we go by the theorem. So for the given system, the triplet ABC is controllable and observable, and provided the assumption of that bounded input and the I condition of the regressor hold, the parameter estimation law ensures that the parameter estimation error capital I is GUUP. So let us consider a Lyapunov function given by 30. So case one, when switch is closed, that is the time when I condition, that is the initial time when I condition is not satisfied. So using the switched adaptive law, we get the derivative of V dot as shown in 32. So this basically this sigma term, K sigma term, this is very crucial in giving the robustness. This is the sigma modification term in the initial time window when the I condition is not satisfied. So if we upper bound this 32, we get this following inequality, and with further solve it, we get this inequality 34. So we show that we get a uniformly ultimately bounded result in the initial time window. So the moment I condition is satisfied, that is the case two when switch is closed now. And if I condition is satisfied, so V dot can be upper bounded as shown in 35. So here lambda min Q is the minimum eigenvalue of Q. And I have already discussed that Q is the captured value of filter regressor YFF at the moment when I is satisfied. So since I definition says that the switching is done when YFF is positive definite. So definitely Q is also positive definite, and conversely the minimum eigenvalue of lambda min will also be positive. And this delta is the double filter disturbance term when the I condition is satisfied. This is also a constant value. So upper bounding the above inequality, we get 36, where beta is a positive constant. And since we have considered a radially unbounded Lyapunov function, which is common in both the time windows, so we can claim that the overall Swiss system is globally, uniformly, ultimately bounded. So to validate the developed algorithm, following system is considered for simulation. So here we can see that the disturbances are bounded, and important to note that the input signals are exponentially decaying function, which signifies that they are I, that is a finite energy signals, and however they are not PE. So looking at the simulation results, the plot shows parameter estimation error. So important thing to note over here that the initial time, since the I condition is not satisfied, the response is bounded because of the sigma modification term. And the moment I mean the I condition is satisfied at about time 1.2 seconds. So the response it enters into a bound and steadies after some transients. So overall performance is bounded. So this plot shows state estimation error, which also shows a bounded result. So this is a very important plot which shows the comparison of parameter estimation error norm for classical robust modification. So here it can be seen that once the I condition is satisfied, I gives the superior response as compared to sigma modification and E modification techniques of the robust modifications. So if we look upon the contribution, so the developed algorithm is valid for uncertain systems with disturbance both in the system dynamics and the output relations. And an extended parameter estimation estimator is designed where in addition to the system parameter, initial states which are unknown are also identified. And finally, the IE-based adaptive observer is inherently robust and does not require any robust modification when the IE condition is satisfied as verified in the last this plot. So in future work, so this algorithm can be extended to non-linear systems, and then output feedback control problem can be solved. So these are the publications. So the present work I've submitted in TAC. Yeah, so that's all. So looking forward for your feedbacks and questions, if any. Thank you.